All right, well, welcome back to ZK Whiteboard Sessions Season 3. Today, you'll have me, Guillermo. I guess I'm the chief scientist at Bain Capital Crypto. That doesn't really mean anything. I just do math. But we'll actually have someone much more important, which is Binyi Chen. Binyi is a postdoc at Stanford under Dan Boneh. He was the chief cryptographer at Espresso prior to that, and has done a bunch of work you probably have heard about. Things like Blaze, things like LatticeFold, which we'll be talking about today, and things like BaseFold. So Binyi, feel free to take us away. I know we're going to discuss some different parts of this, so feel free to outline what we're going to talk about today, and then let's get rolling.
Sounds good. Yeah, thank you so much, Guillermo, for the introduction, and it's a great pleasure to be here. Today I'll talk about LatticeFold, which is a folding scheme based on lattices. And folding scheme is a very useful primitive to help proving large-scale statements in a memory-efficient way. So the outline today will be, I'll categorize the part into three sections. So first, I'll give some background about polynomial rings. And I'll use these polynomial rings to build some Ajtai-based commitments.
Yeah, and it's Ajtai, not Ajtai.
Yeah, it's Ajtai.
Always keep on referring to.
Yeah. And after that, after equipping this with these tools, we'll touch upon our primitive to build folding schemes. So we'll talk about folding, and especially folding in the lattice setting. Along the way, we'll see many challenges. So we'll go over some main techniques to build folding scheme in the lattice setting, such as using decomposition technique, and more importantly, we'll cover another very important topic, which is range proof in the lattice setting.
Yeah. I mean, yeah, LatticeFold is interesting, right? Because normally we're either working over finite fields or we're working over some sort of commutative group in the case of elliptic curve or things like that. Here we're actually going to be discussing a generalization of groups, but specifically polynomial rings, which will have some interesting properties in themselves that make them hard. So, okay, cool. I think we're ready to get started. This sounds great to me.
Great. Maybe we can get started for the first section now.
Cool.
So maybe I just erase this. And let's start with polynomial rings.
Sounds great.
So in the last setting, actually, these polynomial rings are very useful, not only because, as you said, it gives better security, actually also gives better efficiency. So polynomial ring, you can understand this as a generalization of integers. So in snark setting, usually we are working over finite field or integers, but actually in the last setting, for efficiency construction, we'll do polynomial rings. So we'll consider mostly about this kind of cyclotomic rings, which is defined to be the integer polynomial divided by this ideal of x to the d plus 1, where d typically is a power of 2.
So yeah, can you? I mean, I think I know what this means, but let's actually carefully define what this is.
So maybe give you some intuition what exactly this means. So you can understand first, this can be understood as a set. Okay, you can understand this as a set of polynomials with degree less than d, right? Because every time you will do this, you do some modular, and you will get some polynomial degree less than d, and all where the coefficients will be integers. Okay, so this is a kind of infinite set. But we also, the nice thing here is that this also is a ring, because we can endorse arithmetic over the set. For example, if you want to do addition, you have two polynomials of degree less than d. You can add them up to get a new polynomial of degree less than d by just adding the corresponding coefficients of every degree. So that is a simple one. But how to do multiplication, right? So the multiplication is slightly less trivial, but still we can define how to do multiplication over rings. So if you have two polynomials, ax and bx, right? Both of them are integer polynomials with integer coefficients and degree less than d. And what we do is that we first multiply these two polynomials over zx, and we get a polynomial of degree larger than d now, right? But that's fine. What we can do is that we can do polynomial division. If you know that this polynomial, we can do division using this. So we can write down this polynomial in the form of fx times x to the d plus 1 plus another polynomial gx. Okay, and this gx is called a remainder polynomial, which indeed have degree less than d. right? And this will be the result of multiplication. And that's another element inside R again.
Right.
So this endorses the arithmetic for multiplication as well.
So another way of seeing this, maybe of rephrasing this, is if I have two polynomials each of degree less than d, when I multiply them, of course, I'm going to get a polynomial potentially of degree greater than d, but of degree less than 2d.
Yeah.
And what we're going to do is we're going to essentially take every power of, we're going to get a bunch of powers. Some of them are going to be greater than d. Let's call it d prime. Then each of those powers, x to the d prime, gets mapped to x to the d prime minus d, right? That's what we're saying here, or negative that, I guess, with this.
Plus 1. This is, yeah.
So roughly every time you go above x to the d, every term that contains x to the d gets mapped to -1.
Exactly.
Right.
Exactly.
So that's what we're saying here, and that's what this result gives you right here.
Yeah, that's also a valid understanding as well. Yeah, cool.
Okay. Right, and so we always end up, of course, once we multiply two polynomials, the resulting operation, as you've defined it, always ends up with a polynomial of degree less than d.
Yes. Okay. So this is a ring, and also is, as I said, this is an analog of integer. So we can also define a really useful metric, distance metric for R as well, such as similar as we did for Z. So we can define a norm for R as well. And today I'll focus on a special example of infinite norm. So for example, you can define infinite norm of elements in R as the following. So given a polynomial ax, which is a0 plus 2ad minus 1, xd minus 1, the infinite norm of this is defined to be just the maximal value I from 0 to d minus 1, the absolute value of ai. Right. And you can trust me that this satisfies all the property of norm, such as triangle inequality and so on. And this will be very useful later when you want to analyze the hardness of some problem and reduce this problem into some lattice problem. And this is something that I think Vadim has mentioned in last week as well.
So very quickly, right? Yeah. So norms satisfy whatever triangle inequality. For rings, do they need to satisfy anything more for it to be a norm? Right, we have homogeneity, so if you scale, so we can think of a0 to ad minus 1 as a big list of elements, a vector, in other words, of size d.
Yeah. Yes.
The norm is the max norm, which is a common norm.
Yeah.
Certainly it satisfies triangle inequality, homogeneity.
Yes.
Right, and self-reflectiveness. In other words, if a thing equals 0, then the thing itself must be 0. Does it need to satisfy anything else in the case of a ring, or is that enough?
I think it's just the same definition.
It's the same definition as for vectors.
And also there are many ways to define norm for ring as well.
Yes.
You don't need to consider infinite norm. We can consider L2 norm, LP norm, L1 norm as well. So just for simplicity, we consider infinite norm today.
Okay, perfect.
Okay, so this is about polynomial ring, and similar to in the integer setting, usually we are not doing integer arithmetic in Snarks. We're doing finite field arithmetics by modular some prime q there, or like a power of 2. We can do exactly the same thing in the ring setting to make arithmetic more efficient. So that's why usually typically in CPU or in GPU are doing arithmetic over RQ, which is defined to be these quotient rings or residue rings, which is R divided by QR. So you can understand this as very similar to R, except that these are those polynomials with degree d for which the coefficients are mapping to this small interval, or at least represented as ZQ, which is this defined to be this interval of minus Q half and Q half intersect integer.
Sure.
So that means that every coefficient now is mapped to this small interval, or this like ZQ arithmetics rather than integer arithmetics. And that makes much easier to store, much easier to do arithmetics.
Got it. Okay, so yeah, we have like 4 things here. So we start with the polynomials. So this is like any polynomial which has integer coefficients. We essentially now do this modulo, right, over this ideal. In other words, it's just claiming that any term x to the d becomes -1, or another definition is this. And then what we're going to do is we're going to take this r, right, and we're going to take a second modulo,
yes,
which is modulo q times r, which essentially says, in other words, every time, we need to carefully define like what addition means here. I'm not 100% sure. But
so you can understand this as 2 times like sequential like first you can define arithmetic over R, and after that you can do another modular. And what you do modular is just modular every coefficient with Q, and that's done.
Okay.
Yeah.
So exactly. So we're just essentially now performing not just polynomial multiplication. When we multiply polynomials, we get modulo this, but now every time you also add coefficients together or multiply coefficients together, you also take modulo Q.
Exactly.
Right. And Q here, and very importantly, is not a prime.
Yeah, it doesn't have to be a prime.
Right.
And however, in sum of construction, in order to make some property holds, you have to make it a prime.
Right.
Yeah.
Right. So in our case, Q will be a power of 2, which is decidedly not prime, and so this,
So D with a power of 2, but Q.
Q is distinct from D.
Q is a modulus.
Got it.
In our construction today, will be a prime.
Okay.
Yeah.
Okay.
But in general, can be anything. Yeah.
Interesting.
Okay.
So
that's about polynomial ring, and I want to mention another thing. That's like we have a very good efficiency property for RQ. So maybe I can erase the R parts.
Sure, go for it.
Okay. Yes.
Up to you.
Yeah. So there's a nice property about RQ in the sense that first we can pack multiple ZQ elements into one RQ element. That's pretty natural. Like one natural unpacking is just that you have the ZQ elements, you map them to the coefficient of polynomial. And second is that we have really fast multiplication. Fast multiplication over RQ. So given two polynomial, we can compute the multiplication of the polynomial in a much faster way. And essentially the complexity is only OD log D ZQ operations.
Right, and that's just the observation, I assume, that polynomial multiplication is the same as convolution, so you can take the Fourier transform, get pointwise multiplication, and then Fourier transform back.
And another way to view it is that you can understand that for every polynomial, you can define the coefficient vector of a polynomial, right? So coefficient vector of A is in ZQT. And you can understand, as you said, the polynomial multiplication is just convolution. And essentially, the coefficient vector of A times B is just the convolution matrix of A times the coefficient vector of B. And this convolution matrix looks like something like this. So it's a
circular matrix.
Yeah, it's anti-circular cyclic matrix, which is A0 to AD minus 1, and minus AD minus 1, A0 to AD minus 2, so on, minus A1 to A0. So this is a matrix of D by D. So naively, it takes D square operation to compute this matrix vector multiplication. But because this is so structured, you can use some like FFT or other algorithm to make this matrix vector multiplication much more efficient in D log D time.
So yeah, quickly speaking maybe a little bit more about this, is the observation here is, of course, you can treat much in the same way that we were talking earlier, right? You can treat the coefficients of this thing as a vector. These are equivalent views.
Yes.
And certainly now we actually can really say what this means, right? This also means not only when we take the L infinity norm of polynomial, we are actually taking it's the same exact thing as taking the L infinity norm of the coefficients.
Vectors, yeah.
Yes.
But here, when we do ZQ, we cannot define infinite norm, but when it's Z, we can.
Yes. Yeah. We have ZQ is like this norm is like in some sense depends on exactly how we choose these I don't know what's called representative elements or something.
Okay, cool. So that's all the background I want to talk about polynomial ring, but the question is why it's useful, right? So I will then give you an example on commitment. So last time Vadim has talked about how to construct an Ajtai commitment in integers, and turns out there's a variant that's much more efficient than that using polynomial rings.
Interesting. Also, by the way, feel free to write also here if you'd like, or anything of the like. The board is all yours.
So maybe I can write there.
Yeah, I'll try to.
Yeah. Okay. Cool. Okay. So let me quickly remind you what Ajtai commitment is, since Vadim has already explained this in the last episode. So in the Ajtai commitments, we have a data vector which I write it as a long vector f, which is integer vector of length m. Okay, and moreover, in this Ajtai commitment setting, we have some extra constraints that the norm of f should be less than some bound. For example, we set it to be the bound b here. Okay, and our goal is to commit this string and compress this long string to a short string. And the Ajtai commitment idea is that we can randomly sample a public matrix A, which is a uniform example from ZQ and n times m. Where n is some parameters that you can choose depends on the security level you want. And then you do this arithmetic and more q, and this will give you a commitment, which is in ZQ n. Okay? And typically, n is much smaller than m, and typically in practice, n can be 500 or 1,000. Okay? So it has many nice properties, such as compressing and binding. Binding means it's hard to find two different vectors that map to the same commitments. And third is kind of homomorphic, because these are linear operations. But this is not widely used in practice, mainly because the complexity of computing this is not very good. Like it takes about n, m, ZQ operations, right? Because it is there's a matrix vector multiplication which takes n times m. And n, as I said before, in practice like 500, which is pretty large. So actually, it turns out that we have a better way to do it. This is called SWIFFT. The SWIFFT.
Yep.
And the idea is actually very similar to this. So let me explain to you how does it work. So first, you can understand this as same kind of data f here, okay, which is an integer of length m. But another way to understand this is to partition it into many chunks, right? Where every chunk consists of the integer s, okay? And with these c integers, you can understand it as a single ring elements, right? So the other way to look at this, to understand this as a vector of ring elements of length L, where L is m divided by d, right? And now we want to commit this ring vector, and we do something exactly very similar as before. But this time, we sample a random matrix over RQ with dimension kappa times L, where kappa now is defined to be n divided by d. Okay, and I do arithmetic modulo q, and I get another commitment over RQ kappa, which is of the same length.
Are there any differences in security between SWIFT and the standard Ajtai commitment, right?
Yeah,
because here,
exactly.
obviously, this is uniformly random. This is obviously much more structured here, right?
This is much structured. Exactly. So, that's a very good point. So you can understand this as a special case of this, where this is a more structured random matrix rather than fully random. But it turns out both of them can be reduced to some kind of lattice problems. But this can be reduced to some kind of more structured lattice problem for the ideal lattice problems. But those kind of problems also believed to be quite hard. At least for now, we don't see any good, better attacks than attacking these more general lattices.
I see.
So that people believe this is still post-quantum secure.
Got it.
But it gives us a lot of advantage in terms of efficiency.
So just really quickly, so that this problem is hard. In other words, finding two different things that hash the same thing is hard because it reduces.
Small norm, by the way.
Sorry, very importantly, small norm, because it reduces to the what is it?
SIS.
That's right.
Shortest integer solution assumption.
Okay.
Which are finding some short vector such that it lies into this lattice, which is a lattice that makes sure that this vector A times this vector equals 0. Yeah. And here is similar, but the only difference is that A is a ring matrix rather than integer matrix.
All right.
Okay.
Yeah.
So that's it. And why we care about this? Because the complexity of computing is much faster. It takes about n kappa L ring operations. Okay. And if you look at it, one ring operations is only take d log d ZQ operations. So this is n d m d d log d ZQ operations. And this is much faster than this. For example, if you set d to be n, and this will cancel out, and this will cancel out, and this will be m log n, right? So this will be about n log n ZQ operations.
Right.
And this is much smaller than n. If we go 1,000, this go to 10. It's like 100 speed up.
Right.
Yeah.
So one thing here, right, is obviously this is the case where d equals 1, is this up here.
Yes.
So my guess is as you make d larger, you end up with kind of slightly weaker security guarantees.
Yes.
Would be my
okay. Yes. Like there's a trade-off, right? There's a tuning parameters.
Sure.
And in the middle is called module lattice problem.
Okay.
In the extreme is called ring lattice problem.
Sure.
In the most general case is integer lattice problem.
Sure.
And yes, and another way to understand this matrix multiplication is that you can understand it as convolution matrix of A, like root A times F, where F becomes integer. So maybe I write here is like, maybe just F equals Cm. Well, now this rotation matrix A is just a dimension of ZQ and M. Well, it consists of several submatrix, right? Where every submatrix is the rotation matrix of Aij there. So there's another way to view this kind of multiplication in the language of ZQ as well. So that's something I just want to mention, that later we might be, this kind of view can also be useful later. Okay. I think that's all I want to cover in this commitment setting. And next we'll see something that's more exciting, that how to build a folding scheme using this kind of commitments.
Right.
Yeah.
Very, very cool.
So let me start by recapping the notion of folding scheme very quickly, because I think in the season 2, Albert has mentioned this as well. So what is folding? Folding is a primitive that has been introduced by Nova and another paper in 2021. So this is Nova, and there's another concurrent work by a group from Berkeley and Stanford. So they are defining these folding schemes. So intuitively, the idea is we want to check the correctness of two statements, and we run a protocol to reduce the checking into a single, simpler statement. So slightly more formally, suppose you have some statements you want to check which involves an instance x, x1 and w1, for which you want to check that is in some relation, say R, which we'll define later. And you have another statement, x2, w2, and you want to check it is in another relation, say R star. And your goal here is to run some kind of protocol between a prover and the verifier, or in the non-interact case, it's just a proof. So in this protocol, the prover and the verifier will run some public coin protocol, means that verifier will only send some random coins in every round. And they both know the instance, x1 and x2. And the prover additionally know the corresponding witness, w1 and w2. And at the end of this protocol, if verifier accepts, then the verifier will convert these two instances into a new instance, x. And at this point, now it suffices for the verifier later to check that the prover knows a witness for this instance x, which is w, that is in a new in the relation R star. Okay, and how to get w? The prover will just convert these two witness before into a new witness here. So that's
the idea essentially is you have a bidirectional here, right, where it's this new instance essentially fits here, roughly, if and only if with some probability of error, each of the original instances must have been satisfied in the relation.
They satisfy some property very similar to snarks. For example, completeness. If the inputs are correct, then output will be correct.
Certainly. And
soundness or knowledge soundness. If either one of this is incorrect or prover doesn't know the witness for the corresponding statements, then either a verifier will reject or the prover will not be able to prove knowledge for this new instance. So that's called the soundness or knowledge soundness. And moreover, it satisfies succinct property, meaning that its verifier complexity should be very small. So the verifier complexity should be sublinear in the size of the sum of the witness in the input statements. So these are some property we need for folding, and it turns out to be a very powerful primitive for us to build some memory efficient and scalable snarks. But I won't talk too much about application, but our goal today is to build such a really powerful primitive for us in the lattice setting. Okay, so also I want to mention one more thing. In general, typically, this R should be an NP-complete relation. So that we can fold for arbitrary kind of computation we want to prove. So typically what you do is that you have some computation, you translate it into stapling in R, and you absorb it using folding scheme. And such kind of example including Plonkish constraint system, or CCS, or R1CS, and so on.
Right. Yeah, sorry, let's just even take a quick step back. R being NP-complete essentially means you can reduce any verification of like a NP-complete problem, therefore all of them, into a checking that the instance R, like something is within this instance R, right, or satisfies this like particular inclusion constraint. Okay.
Yeah, and this R star is called a accumulated relation, or I call it ACC relation. And how to define it really depends on what kind of scheme you are using. It's different for every different kind of scheme you are using. And today, however, we will not build a full-fledged folding scheme. For simplicity, we'll focus on the toy example. Well, we'll just set R to be very simple relation, which is called a commitment opening relation, which I denote by RCM and B. Okay. So this is a relation for which the instance is just a commitment, a SWIFFT commitment.
Okay.
Q kappa. And the witness is the corresponding opening or a vector F in RL. And it is in the relation if first we have some public matrix we have sampled, right? So A times F mod Q equals CM. This is the first check we want to, this first statement we want to check.
Sure.
And second,
it says that your witness actually, is indeed like hashes or Ajtai commits to the commitment.
Yes.
I don't actually know what to call that.
Yes, it's a valid opening.
Sure.
Like that. Yeah. And additionally, you also want to make sure the norm of F is not too large.
That's right.
And it's parameterized by this value B here. Okay. And our ideal goal would be to build a folding scheme that's given two statements, CM1, F1, and CM2, F2, and we want to reduce the checking of they are in this RCMB to the checking of a single new statements in RCMB. So a new CM and F in RCMB.
I mean, potentially we might want to have some like additional information, not just this, right?
Yeah. So in the final scheme, we are not actually, this will be slightly different.
Okay.
But I will get that later. So for now, let's assume that the dream goal is to merge two statements into one statement.
Okay, sounds good.
Okay, so when it comes to do a folding, the first idea comes to mind is always random linear combination.
Yes.
It's always a random combination.
Here, feel free to.
So let's consider a naive attempt, like kind of a variance of this elliptic curve-based folding scheme into the lattice setting and see how it works. Okay, so let's try to build a protocol. The instance consists of two commitments, CM1 and CM2, right? And additionally, the prover also knows a witness, which is corresponding opening F1 and F2. So the prover knows instance and witness, and the verifier knows the instance. And the verifier wants to check the prover knows corresponding witness. And the very natural way to do this is to let the verifier sample a random challenge. So for example, we can sample a challenge from the interval ZQ, which is minus Q half, and which is also a subset of integer you can understand. And also the integer you can understand as a constant polynomial in R as well, right? So you can also understand this, map this into as a ring element, no problem. Okay, so you will change, the verifier will send this challenge, and after that, the verifier will immediately try to merge these two statements into one. How? You can just compute CM equals CM1 plus R CM2 more Q. Okay, and correspondingly, the prover might just compute the corresponding opening, which is F1 plus R F2. And our hope is that after this, we can reduce to the problem to checking that CMF is again in the relation. Okay, that's our hope. However, it doesn't make sense, right? Why? Because the key reason is that after this folding, this F will have higher norms. So we have 2 points here. The first is that in practice, Q has to be large. Okay, usually, for example, if you want to have lambda-based security, it should be a really large number so that this interval is large enough so that you will have small soundness error.
Right.
So it will be very hard for prover to cheat. But that also means that this number can be quite large. And that means, in the worst case, the norm of F can be as large as, say, 2 to the lambda times the norm of F2. And F2, it is bounded by B, but it might be approaching B. So in the worst case, this can be as large as 2 to the lambda times B, which is super large. And this even exceeds the threshold for making these commitments being binding or secure. Because as I said, so as usually, if you want to make sure the commitments are secure, you have to make sure that this norm bound is never exceeds some threshold.
Right. It's particularly bad, right? So I'm just going to rephrase, right?
Yeah.
Fundamentally, the problem is when you take this random linear combination, you actually so one of the important things here is a commitment is binding only when the function has, in our case, infinity norm less than B. The problem here is not even in the worst case, right? Like R could be very large in the worst case, but even in the average case, this is pretty large, right? Because in fact, this is not just worst case, it's an average case bound. And the size of this new vector, roughly speaking, will be roughly the average size of Q, right? Which is exponential insecurity parameter, which in the case that you have, 2 instances that are of size B, if you take a random linear combination of those 2 things, then the norm of that new thing, this aggregated thing, will be at least the average size of Q times B.
Yes,
roughly.
That's pretty bad.
Yeah, that's quite bad indeed. Yeah. Okay.
And usually in lattice cryptography, we don't like this kind of set. We choose another set. So the first idea here is that we can replace these Chen sets into a new set, which I call S. Okay. So maybe I'll write this again. Okay. So this S is a subset of R, which I define as follows. There's many ways to define S. I just choose one example. So you can choose S to be the set of polynomial in R for which the infinite norm of G is less or equal than 1. Essentially, these are the set of polynomial whose coefficients are just 0, 1, or minus 1. Okay? So it has 2 really nice features. First, the size of S can be as large as 3 to the D. Right? Because every coefficient has 3 options, and they have D choices for coefficients. So this is large enough as long as D is, say, linear to the security parameter. And another nice property is that now the norm of F is much better. So first, the norm of F by triangle inequality, this is less than the norm of F1 plus R F2. And on the other hand, because R is chosen from these sets, it has only minus 1 or 1 or 0 coefficients, and I can actually prove that this norm is never larger than the degree of the polynomial times the norm of F2. Okay, this will be less than...
Right, and that's because you could imagine you get all ones or something, and then all of the coefficients are the same sign. So there is some term in the expression where all of these terms get added together. If they're all in the same direction, you end up with D times norm of F2.
Exactly.
Norm of F2.
Yeah. Okay. That's a very good example. Cool. So, and also we have a bound for F1 and F2.
Right, naturally from the commitments.
So that means this bound is less than about D plus 1 times B, right? And this is much better than before, which is exponential blow up. Okay?
Yes, certainly.
And also, actually, if you set B to be small enough, it's fine to do a one-time folding. Like D plus 1 times B is still relatively small, and still we can make the commitments secure. But however, in the folding setting, we really don't want this. We really want more, even better. because if you have this, that means after each time of folding, the norm will keep growing.
Yep.
At some step, we will exceed the threshold of security. And that means you have to really set a large modulus, Q, in order to tolerate enough number of folding steps, which is pretty bad. So our dream goal is that whether we can have a folding scheme for which we never need to increase the norm, can we just end up with a witness for which finally the witness still have a norm less than B. So that's our goal, and that will come to our first technique called the decomposition. So maybe I erase that part.
All you.
Yeah.
So just really quickly, actually, just for my own sake, roughly how large in practice, we know M and N in the commitment, how large is Q and D roughly? Because D is a power of 2, right? So it's actually could potentially be quite large.
You want to have some concrete parameters.
Yeah, just out of curiosity, like what do you even use in the paper?
Yeah, in the paper, we typically D in the practice is either 64 or 128.
Okay, so it's pretty small. Okay.
Yeah, it's 128, something like that. It's not like 1,000.
Okay.
B is about, like, you can support 2 to 16 or something.
Okay.
And Q, because we want to make Q to be not too large so that we can support really fast arithmetics. So usually we're using 64-bit primes.
Got it.
Yeah.
Got it. Okay.
In some setting, you can even use 32-bit, but in our setting, for some certain reasons, you cannot support 32-bit primes yet.
Okay. Yeah. Interesting.
Okay. So now the first technique is called decomposition. And actually, this is a very simple technique and is also widely used in the field of homomorphic encryption. But it turns out it's also very helpful and useful in the proof setting as well. And let me give you some like very quick intuition what it means. So say we have a number, okay, like 8. I feel it's too large, okay? I want to make it even smaller. So one way to do that is to set up some base. For example, base is equals 3. Then you can represent 8 using base decomposition. You can represent as a pair of value, which is 2 plus 3, 2, right? So this tuple or this pair of 2 and 2 can be used to represent this number 8 as well under this base. But nice thing is now this pair of values are much smaller. And similar things holds for polynomial as well. Okay. For example, if you have 8 plus 7x plus 6x squared plus 5x cubed, you can write it as 2 plus 1x plus 0x squared plus 2x cubed plus b, which is 3, of 2 plus 2x plus 2x squared plus 1x cubed. So you can split this single polynomial using this algorithm into 2 polynomials for which the coefficient of these 2 polynomials are much lower than before. And you can extend this idea to even a vector of ring elements, right? You just do this decomposition for every polynomial without problem. So that's the high-level idea. And with this in mind, now let's see how we can improve this scheme and make it better, okay? So again, we have this, let me just write down again. We have CM1, CM2, W equals F1, F2. And verify has instance. The prover has instance and witness. Okay, and before we do random combination, the prover now will do some preparation. Okay, it will decompose this vector I equals 1, 2, 2. It will decompose Fi into, say, 2 vectors, which such that FIL equals, say, square root B FIH, where square root B is, let's assume square root B is an integer, okay? Okay. And after that, you will commit these 2 vector, these 2 decomposed vector, and you have 4 decomposed vector now, and you will send these 4 commitments to the verify. And the verify will first check that these 4 commitments are consistent with these 2 commitments by just checking that CMI equals CMI L plus square root B CM IH. This is good because the commitment satisfies kind of linear homomorphic property. And now if this check holds true, then it's reduced to a new problem for checking that the prover knows some really no-norm vector, decomposed vector, for these 4 commitments. However, this is 4 statements, right?
Yes.
What we want is 1 statement. So at this point, a very natural idea is now, let's go back to the original idea for randomly combination and to verify with example RIL and RIH from this challenge sets S. Okay? And after that, you just do the same trick. And verify will combine all the 4 commitments into 1 using this random combiner, which gives you a new commitment CM. And verify will do something similar, but at this point, given this 4 decomposed vector, you also use this random combiner to combine them together into a new vector F. And now I claim that after that, we do have this new instance and this new witness is inside the relation of RCMV. Okay? Why? Because I claim the norm of F now is much smaller. So first, it satisfies this matrix vector multiplication relation, which is simpler to check. The key point is like I also can check that F is having much lower norm. Why? Because, let me erase this part. Because we have that the norm of F is the random linear combination of FIL and FIH, right? So by triangle inequality, this is less than 4 of the maximal value. Well, I is in 1 or 2, J is in low and high of what? Of Rij times Fij, right? So we have 4 decomposed vector, and we have 4 randomly combiner term, and which gives you F, and want to check the norm of F. And as the argument we had this before, Rij times Fij is always smaller than D times Fij. It's norm, right? This is the same argument we had before. And finally, we also know that this Fij is less than or equal, less than square root B, right? So that means if you sum them up, you get that the norm of F is less than 4 times D, I think it's less, 4 times D times square root B.
Right.
And then if you choose B to be large enough, for example, 16D squared,
4 squared,
right. 4D squared, then this is less than B, or less or equal than B.
That's right.
So you end up with a witness that's lower than norm B. Okay? So
very interesting. Okay.
So that's pretty nice. It gives you a protocol that satisfies the completeness. Like given 2 correct input statements, you output 1 correct input statement. Right. However, the bad thing here is that we don't know how to prove it's secure.
That's right.
And I'm not saying that actually I have concrete attack to this protocol. For now, we don't have any concrete attack. It's just we don't know how to prove it's secure.
All right.
The key reason that we don't know how to prove it's secure is because in this case, the malicious prover might not bind his input witness to the commitment, right? We have no way to guarantee that prover is enforced to bind some no-known witness F1, F2 to CM1, CM2. So that makes it necessary to add something more to ask the prover to show that they do know some F1, F2.
Right. Like the problem is we are currently violating the condition that indeed we have no idea if Fi, or these FIL and FIH, are the correct decompositions corresponding to this thing. Certainly, if they are the correct decompositions, right, then you have this, you get the result, right? But we have no idea if FIL and FIH are actually small norm.
Yes.
And specifically, there's norms smaller than square root of B,
exactly.
right? That's the problem.
Exactly.
Okay.
Exactly. So that's why we need some extra tools for enforcing, or actually to extract some witness FIL, FIH, and F1, F2 out from the prover that satisfy the input relation. So that is something we call range proof. Okay, and we'll cover that soon.
Cool.
Yeah.
So range proofs.
Yeah, range proofs. So before I start explaining how LatticeFold do range proof, I want to, for those audience who are already familiar with background, I want to help them ask one question. Okay. So do we need to reinvent the wheel, right? Can we just use existing techniques? So in the literature, we do have many range proof or lookup arguments, and I would categorize them into two parts like that are most relevant. The first one is those lattice-based range proof, such as lattice-based Boolean proof. Like there's an extension of Boolean proof to lattice setting, and we also have Labrador, which is a like a proof system in the lattice setting that gives you some range proof using random projection. However, they are not quite fit for the folding setting. If you remember, in the folding setting, we need the verifier to be sublinear, right? Have really nice complexity. But all those kind of construction needs linear time verifier. Okay, they do need linear time verifier, so we cannot use that kind of solutions. And the second category are those more snark-based, like poly-IOP-based, like pool lookup, CQ, and so on. And all these kind of techniques will be not that fit for lattice setting, however, unfortunately. The reason is that those kind of construction needs the prover to provide some auxiliary vector, which are actually high norm. Usually they are high norm. So in the lattice setting, if you want to send the commitment to them, you have to do decomposition again and send the lattice commitment to it and prove there are no norm. So you start with some problem that you want to do range proof. You end up with the problem that's same, like as hard as before. And you have some circularity issue. So that's why those kind of solution is not also not very fit for this setting. So that's why we need to kind of come up with some new solution. And the first solution I want to mention is called LatticeFold. Okay.
So finally, the title of the paper shows up in the movie, you know.
Yes, finally the title shows up. And actually, I would call it LatticeFold's range proof because there is an end-to-end system. So at a very high level, our goal is the following. So we start with some statements. We do have some strict norm range check in the statements, such as our definition of RCMB, right? In this statement, we do have some strict check that the norm of F is lower than B. And our goal is to come up with some protocol that finally, after this protocol, we can reduce these statements into much simpler statements. That will be something like X equals same commitments, but something extra auxiliary information, and W is still F or something else. But anyway, in the output, we need to check some new relation. Well, this new relation is much simpler than before and does not require any range proof anymore. Okay. So that's our goal.
Sure.
So now the question is how to do that. And LatticeFold provides one way to do that. And let's see how it works. So at a very high level, it consists of two main steps. The first step is to use the decomposition trick we had before. So let's say we start with some norm bound B that is actually pretty large. And I didn't notice by 2 to the t. Okay. So the first step is that the prover will decompose this vector f into t vector. Okay. So you will decompose and use some algorithm to generate f1 to ft such that f equals f1 plus 2f2 plus 2 to the 2f3 to f2 to the t minus 1 ft. And all of these factors are now much no norm. So their coefficient is only 1 or 0 or minus 1. And they will send commitments to the verifier, and the verifier checked commitments is consistent with the input commitment. And then after that, it now suffices to check these t different statements. Check CM1, which is the commitment to F1, F1, is in this new relation, which is RCM2. Okay, because now we only need to check F1's norm is less than 2. And similarly for all the commitments and the vectors. Okay. So the reason we want to do the decomposition is because this relation is much easier to prove. Because we go from some large B into smaller 2. And I claim that there is a very efficient way to batchly prove all these statements and merge them, reduce them into a new statement, which is of the form I said before. So it's of the form of something like a new commitments, CM, and some other values, like there's a R, which is vector, and a V, which is value, and W is some new vector F, such that this XW is in some new relation called R ling B, or maybe not B right now. So there's a linear relation. And this relation is just checking this matrix vector multiplication relation and some other evaluation statements, like F evaluate at some point R equals V. Not that important.
Okay.
Yeah, and also some other very, very relaxed norm check rather than some strict norm check. So after that, you end up being able to reduce this statement into a new statement that's much simpler to fold. But how to plug in this? So next, I need to do 2 steps. First, I explain how to go from this to here. Right? That's the batch proof step. And second, given these kind of tools, I want to mention how do you plug in into the framework we had before and obtain a folding scheme. Okay. So let me do the second step first. Okay. So the idea is very similar to this.
So sorry, just really quickly, the second step here is going to be we already have some way of batch proving this. How do we use this to construct a folding scheme?
Exactly.
Okay,
exactly.
Perfect, great.
Yeah. So the idea is actually pretty similar to this framework. The only difference is that we have 2 inputs rather than 1 input.
Okay.
Right? So what we need to do is actually we go from CM1 F1 in RCMB and CM2 F2 RCMB, and we want to go to this, right? So actually, because we want to have a folding scheme, so actually this relation has to be the same as this, but this is just some like a modification, which is not that important. And how to do this? You just to do this like twice or in parallel. So you go from CM1 F1, CM2 F2, and decompose them separately, and this will goes to 2T statements, which is CM11 F11 to CM1T F1T.
And then similarly for CM2.
Yeah, and similar for CM2, and finally CM2T F2T. And then this is no difference. It's just here they have T statement, here I have 2T statements. You just use the same trick to merge them back into a single statement in R-ling. And this gives us a way to do the folding. And the only difference here is that you have to make this to be R-ling as well, but that turns out to be fine. It's not that complicated.
Okay.
Yeah. So now the rest of the question is how to come up with this batch proof protocol, right? Okay. Okay, so our goal is to batch proof T statements in RCM2. Right? That's our goal. But let me start with some simpler problem. Okay, let's just focus on proving 1 statement in RCM2. Okay, at the moment.
Okay.
So we want to prove that CMF is in RCM2. And let's recall the definition of RCM2. Okay, if you still remember, this is a set of relation where the instance is a commitment in RQ kappa, and witness is a vector in RL, and we want to check that AF mod Q equals CM, and the norm of F is less or equal than 1. Or less than 2 is the same as less equal than 1. Okay? And there's another way to view it in the language of integer and ZQ. As I said in the very beginning of the talk, it's equivalent to view it as another relation, right? Well, you can view this instance with the commitments as an integer vector, or not integer vector, ZQ vector, which is ZQ to the n, right?
Yes.
And also W is...
That's because, like n you have defined as being k times d or something, right?
Yes. Yeah, just consider the coefficient vector of that. And F can be understood as an integer vector of length m. And we want to prove that the rotation matrix or the convolution matrix of A times the vector F mod Q equals Cm. And similarly, instead of checking the norm of polynomial less than 1, just checking the norm of vector is less or equal than 1. Okay? And then we use this very simple trick that what does this mean? This just means that every element of this vector is inside a set of -1, 1, and 0. So we can rewrite this as checking for every I in M, Fi times Fi minus 1 times Fi plus 1 equals 0 mod Q. Right? And it turns out this, I think, is definitely holds true when Q is a prime. It's less clear because there's some 0 divisors that make it less clear when Q is not a prime.
Yes, for sure. Yeah, because when Q is not a prime, you have other problems. When Q is prime, this is a field.
Yes.
Right, and so you're totally good.
Yes. Okay, so given this is a so-called zero-check relation. Unfortunately, I won't have time to dive into the details. But I want to tell you that given this zero-check relation, there exists a very efficient reduction to reduce this into a much simpler relation using sum check. Okay, so sum check is another rabbit hole I won't cover. But if you want to know more about detail of sum check, check the season 2.
I think season 2 has it. We might have an episode.
I think Justin Taylor has an episode for that.
Yes,
and you can check Justin's episode there. But by running this very efficient sum check protocol, you can reduce this relation into a much simpler relation, for which the relation now is become a linear relation that adds some kind of evaluation statements. So there's R and V, and W is the same as F, and you check the same rotation relation and some other relaxed norm constraints. But moreover, you only need to check that some kind of evaluation of F. You can understand F as a vector, but also some polynomial, and its evaluation at point R equals V, something like this. And this turns out to be much easier to fold, and that's our target, right? As I said before, our goal is exactly reduce them to a much simpler relation that has no strict norm check anymore. And it turns out, if you want, it's very easy to extend this idea to the batch setting.
Sure.
Because, okay, so I have to mention this sum check is a very nice protocol that is also very batching friendly.
Yes.
Essentially, what it can do is it can combine all these sum check instances into one instances and run a sum check and get a single statement. So that's the basic idea. Actually, this is the idea I think is more similar to the follow-up work of Neo. So both Neo and LatticeFold are using some kind of similar framework for doing this range proof. And I'm actually using their kind of language because I think it's much easier to explain. For LatticeFold, initially, they are using a more advanced Chinese remainder theorem or number selection.
I see. Sure, yeah.
That's more complicated, but this is much easier to understand.
Nice.
Okay. So this is the first idea. However, if you look at it carefully, you find that this is actually not that good. Okay? Because if you look at this, the prover needs to generate many commitments beyond this single commitment, right? So actually, the prover complexity of LatticeFold is roughly about 2T commitments. Okay. you have to additionally generate 2 T commitments, which is actually pretty expensive. And beyond that, you also need to run some sum check, okay, which is also not negligible. But even just consider this. This is already much more complex than just computing one single SWIFT commitment, right? So this is not very good when T is large. So for large norm ranges, this is actually not that efficient, even though it's still very practical.
Sure.
But it's supposed better when T is extremely small. And that means this is a perfect solution for this application where you want to capture Boolean arithmetics or something like that. But, yeah.
Okay. Yeah, so the fundamental problem here is like, look, we've reduced the problem into like 2 T instances of this, problem, which is obviously like certainly substantially harder than the original statement. I mean, we now have the we do have the constraint for this less than B now, which we can guarantee for each of these. But
the point is like this is much easier to prove, but the prover needs to first provide these commitments to M1 and M3. Even just computing them takes a lot of time.
That's right. Yeah.
And you have to do that because otherwise you have to a really high degree relation that makes sum check really expensive. You want to make sure sum check not that expensive. So it turns out there's an even better idea. Recently there's a new paper called LatticeFold Plus. Okay. So even if you call it plus, actually the idea is quite different. So what it has is that the main contribution of this paper is that it gives a new direct range proof. So it's a more direct range proof.
I assume, right? Because here we're not using any properties of rings, right?
Yeah.
Here we're just kind of fully saying, look, you can certainly take a thing, decompose it into bits, or plus, minus, 1, and 0, I guess. So trites? I don't know what they're called.
Ternary.
Thank you. Ternary representations, right? And sure, yeah, fine. You can take a hammer like sum check and reduce it to a linear relation. But look, we have a lot of structure going on here, right?
Exactly.
We're working over a ring. We have a bunch of nice properties of that ring, which we did not have previously. So, okay. And so the observation of LatticeFold Plus is you can actually use that structure to construct a range proof for these folded instances.
Exactly. Very good observation. And let me give you a little bit more intuition about that. Why is like what kind of algebraic structure we are using for RQ to enable us to get a better range proof. So for that, I need to compare a little bit in the setting of ZQ and RQ. So in the setting of ZQ, if you want to represent a range proof statement, like something like I want to check the X is in some range, for example, a set of 0, 1, 2 to D minus 1, let's say. Okay, this is a not ternary. This is a larger set, but D is usually much larger. Then what I can do if I don't want to do decomposition, the only thing I can do usually is just to check this degree D formula are holding true over ZQ, which is checking X times X minus 1 times X minus D plus 1 equals 0 mod Q. Right? This is what you can do. You can translate this statement into algebraic statements, but this algebraic statement is really high degree.
Yes.
So that means if you run a sum check, you really run a sum check over a high degree polynomial, which is actually pretty expensive.
Correct.
So that's why we need to do decomposition. But if you are doing things in RQ, for representing the same statements, you can do much better. So let's say your goal is to still represent X is in 0, 1 to D minus 1. I won't go into the details, but my claim is that you only need to some kind of degree 2 formula over RQ to represent this. Okay, that's something I won't cover. You can look at the paper if you want to take a look. But the nice thing here is that even for checking some larger ranges, we only need to do something very simple, low degree, and the sum check can be much low degree and much more efficient. And there's even more optimization in the sense, naively, this will translate to a sum check over RQ, right? Because this is an equation over RQ. But turns out that these formulas are so structured, we can actually reduce this to a sum check over FQ.
Oh, that's neat. Okay.
Over ZQ, but in our case, it's actually FQ. Q is a prime.
The field.
And this cost is actually minimal. It's very small.
Interesting.
So actually, the cost it will be something else. Like finally, the prover time is about one so-called double commitments plus one several sum check over field. And this part is actually pretty small. And this part is also pretty fast. The cost is approximately just 1 or 2 SWIFT commitments, which is way better than 2T commitments. So that's why it can lead to an even more efficient range proof for a large range B here.
Do you have any intuition here for why this is true? Just like at a very high level even?
Okay, sure.
Also happy to, if you want to come here or whatever.
Yeah, maybe I can go here a little bit. So this is kind of a bonus
Yeah, I'm just curious, you know, I mean, it's also fine if not. I'm just, it's a very magical statement, so.
Yeah. So to check this, you can understand this as a lookup argument, where the table is this. 0, 1, and D minus 1, right? And, okay. So given this, you can embed this table inside one ring elements. For example, you can define Tx to be something like 0 plus 1x plus 2 d minus 1 x d minus 1. Right? And let's for simplicity, let's assume the RQ is slightly different, okay, to make my explanation much easier.
Great.
So this is zx. Actually, the ideal here is x to the d minus 1. So xd is the same as 1.
Yes.
Okay. And now you have a number. I shouldn't use x, but let's say we have a number a. I want to check a is in the table tier, right? I want to check a is in 0, 1 to d minus 1. How to check that? It's the same as saying that a equals the constant term. This is constant terms meaning. Constant term of a multiplication, which is Tx times something else. What should be something else? If you want to extract a, how to multiply a table polynomial t with another polynomial to extract a? The idea is just multiply x to the d minus a, right?
Sure.
So you only need to check this single equation, and this is actually even not degree 2, it's actually linear, actually, because t is some kind of constant stuff. But beyond that, you also need to prove that this one is a monomials.
Sure. So first, before we get to that, right, like the observation here is like, look, the constant term, so take tx, whatever this is, multiply by x times d minus a. Right. Everything is going to get shifted by x to the d minus a, and specifically the term a is going to become the constant term, right? Because every d order term gets mapped to 1.
Yes.
And so this is expressing that relationship here.
Yes.
Okay.
Yes. That is DQ. Yeah. So that means it suffices for you to prove that I know some other polynomial or value, which I say delta x, such as constant term of tx times delta x equals a. But also I want to prove that this delta x is of some special form, which is inside 1x cubed to x to the d minus 1.
Right.
And how to check that? You need to do some other checks, which is degree 2. That's why you need some.
Interesting. Got it.
And that's it. Yeah.
Cool. Very, very cool.
Okay, so that's about the range proof. Yeah. So in summary, we've covered how to build up some commitment from polynomial rings, which is more efficient. And we've touched upon how to build a folding scheme using decomposition technique. And finally, we fixed the proof. We make the scheme secure by come up with some new range proof.
Very, very cool.
That's it. Yeah.
Yeah, well, thank you, Binyi. It's been a lovely, lovely time learning about LatticeFold and everything relating, ideally, and building up to it. But yeah, it's been a lot of fun. Thanks again for having me, and thank you all for watching.
Yeah, it's my pleasure. Yeah,
Thanks.
Thank you so much.